Thank you, Matt, and welcome, friends. Thanks for agreeing to spend your lunch hour eating pizza and hopefully learning a little bit about that. It was working before.
And now it's beeping.
So we'll try it again a little bit. But I'm going to start with a little bit of terminology, then we'll look at the molecular structure of dyes and how that influences our perception of the color. A very brief history of dyes, and then we'll talk about some natural dyes, synthetic dyes, and then a short summary. So, a dye. A dye is an organic substance which is colored and can impart color to some other object to which it is applied. For example, we have something like beet juice. And rather than just let you see the picture on the slide, we're going to get some canned beets. And I have an extra can of beets. I wasn't sure whether 1 or 2 cans would be necessary. 1 can is enough. So if anybody wants an unopened can of beets at the end of the presentation, that can be like the door prize. So, a nice bright red color, and this is just a piece of cotton cloth. We'll stick in there, let it soak for a little bit. Somewhere I brought a pair of forceps to get that out. Aha, here we go. And we'll see whether it actually dyes the cloth. Looks like it, you think?
Yeah.
I hesitate to pull it out too much. But this solution contains a molecule called betadine. And betadine has this structure. I don't want to go too much into the structure right now, but please take note. If you're familiar with chemistry, you know that there are some pretty polar components to organic molecules. And in this case, we've got carboxylic acids, carboxylates, we've got an aminiamine, we've got hydroxyl groups, and so on. Those polar groups allow the dye molecule to actually dissolve in water. A pigment, unlike a dye, is something that's not soluble in solution. Many times pigments are inorganic materials. They can be organic as well, but some of the best known are inorganic. And this is one example, hematite. Hematite is iron oxide, and thanks to the Earth Sciences Department, we have a good example of hematite here. If you want to come up and look at it later, you're welcome to do so. It's just iron 3 oxide or ferric oxide, a nice red color. And so if you take some finely ground hematite and put it into some medium in which it can be dispersed, then you can make a red colored paint, for example. So here we have some white paint, and there's actually a pigment in the white paint. I know you can't see this very well, but if I hold the brush up, you can see the white paint. If I take a little bit of this paint and put it into another jar, you'll notice I do have a covering for the table here. So there we have some white paint. This does contain a pigment. Who knows what the pigment in white paint is?
Zinc oxide.
Generally not zinc oxide. That's the pigment that's in sunscreen.
I'm sorry, I'm not a scientist.
No.
It's all right.
Everybody's a scientist.
Titanium.
It's titanium dioxide. Right, titanium dioxide. Well, thanks to the chemistry program at Adams State, I have some ferric oxide here. It's probably not as finely powdered as we would really like, but if we put that in and then stir it up, I don't have enough to make it a really deep red, but would you agree that it's kind of a pinkish color at least? So let me now So when we apply the pigment, if it's dispersed well enough, we can use this brush and piece of scrap wood, and we can make a nice pink coloration on that piece of pine. So that's a pigment. The difference primarily between a pigment and a dye is the solubility of the material. Last term I'm going to introduce you to is mordant. Now mordant you can think of as a dye fixer. Okay? It's something that assists in the ability of the dye to attach to the cloth and remain attached to the cloth. Mordants, there's a variety of different types of mordants, tannic acid, other acids and bases, but frequently mordants are inorganic salts, metal salts. One example is this, potassium aluminum sulfate, better known as alum. And you can just get alum at the grocery store, that's where this came from. And if I put a little bit of alum into this beet juice, I have to confess I'm not really sure how much to use, but we'll see if that swirls around. Now I'll put a second piece of cloth in there. The alum should make this dye now a bit more color fast. We won't really be able to tell until we wash the cloths, and that's not something that I intend to do here, since that sink is not attached to anything and it would just fall onto the floor. But again, the dye, or the mordant, is just used to fix the dye to the cloth. So here's a typical structure for cellulose or cotton cloth. And when you look at it, you see that it too has polar groups. That facilitates the interaction between the polar dye molecules and the polar functional groups of cellulose. Other natural fibers are proteinaceous, like silk and wool. And then the backbone, we do have these amine groups and carbonyl groups, which are polar and can hydrogen bond or be attracted by dipole-dipole forces. And then the side groups, these R groups, can be polar or nonpolar. And if they are nice and polar, like this glutamic acid residue or the serine residue, then that means that they too will be able to be attracted to the dye, to the polar groups of the dye. So here's an example interaction of the dye with fabric. So there's cellulose. And here is a dye that everyone is familiar with, indigo. It's what makes the blue jeans nice and blue. Okay? And you can see that indigo has polar functional groups here. As it turns out, indigo is not soluble in water. We're going to talk about that a little bit later. But these groups can interact with one another through a hydrogen bonding sort of interaction. And so we've got the hydrogen of the cellulose being attracted, to the oxygen of the indigo. And likewise, we could have the hydrogen that's attached to the nitrogen of the indigo being attracted to an oxygen, and so on. There's many opportunities for hydrogen bonding interactions. And now we want to talk a little bit about the colors that we perceive and the molecular structure of the colors. What we see is visible light, which is just a very narrow band of the electromagnetic radiation spectrum. If we look at this slide and read it backwards, we get the familiar Roy G. Biv that everybody learned in chemistry and physics. The red, orange, yellow, blue, green, indigo, and violet. Wait, did I say that right? Red, orange, yellow, green, blue, indigo, and violet. So the Roy G. Biv, these are the colors that we see. And notice that there are wavelengths associated with each of the colors. Our eyes can see from about 380 nanometers to maybe 720 nanometers, something in that vicinity. The energy increases as we go this way. So the blue light that we can see, or the violet light that we can see, is more energetic than the red light. Remember those wavelengths. Be quizzed on them later. So when we see objects, what we see depends upon what's absorbed, what's reflected, what's transmitted. For opaque objects like these bananas, we see them as yellow, as long as they're ripe enough, and not overripe. But we see them as yellow because yellow wavelengths of light are reflected off the surface, and all the other wavelengths of light are absorbed by the bananas. If it's a transparent object, what we see, the color that we see, is what passes through, or what is transmitted through the transparent object. Think about a lighting for a theater production or a musical group or something of that sort. You put these gel sheets in front of the light, and that's what causes you to see blue on the stage, or green or red, or whatever it happens to be. But all the other colors are absorbed, and the color that you see is what is transmitted through that gel or that film. So colored molecules have to absorb electromagnetic radiation in the visible region, that is between about 380 to 720. And when they absorb in that region, the color that we see is just the opposite. Colorless molecules absorb electromagnetic radiation not in the visible region. So ultraviolet, infrared, or microwave, or gamma rays, or what have you, but just not in the visible region. So let's take a look at a molecule that many of you are familiar with, at least by name, if not by structure. This is benzene. There are 3 different representations here, and the one that I'm going to focus on is this middle one. This absorbs in the ultraviolet region. As a consequence, it is colorless. We do not see color with the molecule benzene. But I chose this because it does have a structural feature that I want to emphasize, and that is the presence of what is called a conjugated system. A conjugated system means that we have alternating double bonds, single bonds, double bonds, single bonds, and so on. Whether in a ring or not, if we have that pattern of alternating double and single bonds, then we have a conjugated pi electron system. Well, that's colorless. You may be most familiar with benzene because it's a toxic material. It's a liver toxin, something that is not good to inhale or get on your skin or things of that sort. But it's a very useful compound for converting into materials that we use on an everyday basis. Here's another molecule that you're very familiar with, if not by structure, at least by name. Do you know what it is? It is beta-carotene. Excellent. Beta-carotene. So this is found in carrots and a variety of other root vegetables and some fruits as well. This, unlike benzene, is colored. It absorbs at 458 nanometers. So here's the quiz. Where is that wavelength in the electromagnetic radiation spectrum? Yeah, in the blue-violet area. And because it absorbs that light, we see the opposite on a color wheel, for example. So if it absorbs in here, then we see this color. Carotene absorbs in the visible region because it has a more extensive conjugated system. There are 11 double bonds in conjugation here in carotene, as opposed to only 3 in benzene. Now this whole string of conjugated bonds constitutes what we would call a chromophore. Chroma from the word color, and phore for the absorption. So in molecules that have chromophores which will absorb in the visible region, then we're going to see a color associated with them. It's not just carbon-carbon double bonds in conjugation with single bonds. that lead to chromophores, though. We can have other groups. For example, in the betadine, you saw some carboxyl groups that had carbon-oxygen double bonds, and the iminiamide, which had a carbon-nitrogen double bond. The exact structure really does affect the color, as you'll see once we get into some of the actual dyes. So dyes have a long history. There's evidence from prehistoric times that Saharan rock desert paintings, or evidence from Saharan rock desert paintings seem to indicate people wearing colored garments. We don't really have any garments that are colored from that time period because, after all, fibers, natural fibers, don't necessarily last in the thousands of years. But the paintings, which probably incorporated pigments from various mineral sources, do show the color. Indigo dyed garment from 3500 BC, found in Thebes. I believe this is Thebes, Egypt, not Thebes, Greece. And that's based on the fact that, well, a little bit later on, we're going to see more about Egypt. Dyeing of silk in Chinese writings from 2600 BC. First certain use of mordants for dyeing cloth in Egypt. The first formal organization of dyers, Collegium Tinctorium, formed by King Numa Pompilius of Rome, back sometime during his lifetime, from 750 to 670 BC. At that time, the dyers were considered subordinate to weavers. So when we talk about classes of society, here you have the weavers, here are the dyers. The dyers' hands were always highly colored. You know, the way that many dyes were processed didn't lead to the dyes necessarily smelling all that good, and so the dyers didn't always smell that good. And weavers, man, they worked with nice clean cloth and created or clean fibers and created the clean cloth and so on. So they were a step ahead. But now look at that. So that's still BC. Until 1856, the only dyes known or used were from a natural source. It wasn't until 1856 that the first synthetic dye was prepared. And we'll come and look at this in a little bit later. So a long time for people to gain expertise doing various experiments on how to create the dyes and getting them to adhere to the cloth. And then in this country, the first book on dyeing was published in Massachusetts in 1798, The Country Dyer's Assistant by Asa Ellis. All right, so now we're going to talk about some dyes. And certainly one of my favorites, because of the attire that I prefer to wear, is indigo. Indigo comes from a couple of different plants. This is the indigo plant, or Indigofera tinctura. And this is the woad plant. It's W-O-A-D, which is Isatis tinctoria. The indigo plant is a more tropical plant, and woad grows in more temperate climates. So in England and Central Europe, for example, woad was the source of indigo. In India and Egypt, the indigo plant itself was used. And in the U.S., when we still had slavery, indigo plantations flourished in the southeastern United States. And since Britain at that time was the hub of the textile industry, the indigo plants were grown and harvested here, shipped to England, then for the dyeing. So indigo itself is the structure on the right, but that's not what exists in the plant itself. What exists in the plant is indican, and indican is a glycoside. That means it has a sugar. I think, Dr. Miller, this is glucose, you think? So glucose attached to this heterocyclic ring. And the way we get indigo, or at least the way it was obtained, was to take the indigo leaves, grind them in an aqueous solution, and let them sit for quite a while, for days. And during that time, a glycosidase enzyme would cleave off the sugar portion of the indican and leave a molecule called indoxyl. Indoxyl is also colorless, but if you take the indoxyl and immerse the cloth in the indoxyl solution and then hang it up, maybe beat on it a little bit to get it to oxidize more thoroughly, the indoxyl gets converted into indigo. And this sort of change of color with oxidation is certainly not unknown. For example, if we take this solution, and this contains a reduced form of the dye methylene blue. And if we can oxidize this, then we can get the color to change. Oxygen, just in the air, is a pretty decent oxidizing agent. So if we just allow a little air to come into this, and then mix the oxygen together in solution, we should be able to get a nice blue color to show up. And so this is what would happen if you were dyeing a piece of cloth by immersing it in an indoxyl solution, allowing it to oxidize in the presence of the air, gives you the blue that we associate with indigo. And that's necessary to do it in those steps, in that sequence, because the indigo itself is not soluble in water. So we would not be able to create a solution of indigo and apply it to the cloth and get the dye to take hold. Alizarin. Alizarin is a really interesting dye, natural dye that comes from the root of the madder plant. And I do have somewhere the name of that. It's something rubium, I think. Rubia tinctorum. So the leaves, or the roots of the madder plant, not the leaves in this case. And they contain the compound alizarin. It's a pretty simple compound. It's 1,2-dihydroxyanthraquinone, if you want the chemical or the systematic name for it. But this is red in color. It's not as big as the betadine, which also was a nice red color, but the presence of the carbonyl groups and the hydroxyl groups, the actual structure really can change the observed color that we see. Alizarin is a dye that works best if you use it with a mordant. For example, alum as a mordant would be good, or aluminum sulfate, or something that contains a multivalent cation. Because the aluminum then can form what we would call a coordinate covalent bond between the oxygens of the fiber and the oxygens of the dye itself. Now that fiber could be cotton, or it could be wool or silk, because serine and tyrosine, as amino acids, do have OH groups. Carboxylate groups from glutamic acid, aspartic acid, and so on would work just as well as the OH group of cellulose. So here's a picture of some skeins of yarn, I think, with that have been dyed with alizarin in different concentrations. There's an interesting little historical note, though, that I found to be pretty that I just needed to share with you guys. So Alexander the Great used madder to trick the Persian army at one time when the Persians were invading Greece. So what he did was make a solution of the madder root, and he dyed the soldiers' tunics with that root. And then the soldiers laid down on the battlefield. When the Persians came, they assumed that everybody was already dead. And so their guard was let down, and at the proper signal then, Alexander got the Greeks up, and they slaughtered the Persians. And so They won a battle because of this dye, alizarin. Well, and probably because the Greeks were pretty good fighters too. Alizarin was a dye that could be made synthetically as well, but it wasn't until 1868 that it was first made synthetically. And from a really fun and interesting book on a practical handbook of dyeing and calico printing from 1874, there's not very many color plates in that book, but this is one of the color plates in there. The top piece of cloth is dyed with madder root, and the bottom is dyed with synthetic madder. Or here it's called artificial alizarin. So alizarin that had been synthesized in the laboratory. If you look at the original color plate, there's a slight difference in color between the two, but they're pretty darn close. And the development of synthetic dyes really put a damper on madder growing and harvesting, because it was much simpler just to create the alizarin in the laboratory. Henna, what do you guys know about henna? What do we use? What is it dyed for? Or what do we dye? Skin, right? So for tattoos. So this is the henna plant. Lawsonia inermis. And this is the structure of the compound that comes from it. Very simple compound. It's called lawsone, 2-hydroxynaphthaquinone. But as you look at it, it does have the conjugation that is required for absorbing light in the visible region. Have any of you ever had a henna tattoo? Okay, I never have, so you guys can correct me about this. This is a picture I got off a website, hennabyholly.com. But you can find anything you want on there. But according to the description, so tell me if this is right, you guys, okay? This is the paste that's made from the henna leaves as it's initially applied to the skin. And then after standing for a while, it gets rubbed off, and this is the color that results. And then upon further exposure to air and oxidation, you get this color. Is that
You should really try it, Marty. There's no commitment involved at all.
That's the good part about it. The only time I had a temporary tattoo was once on Ride the Rockies, and it was just one of those little transfers that you could put on. It was a bicyclist that I put on my calf. It needed about a week, and then it all washed off. This doesn't wash off quite so easily. What I saw was exfoliation of the skin is what's required. So how long did your henna tattoo last?
Probably like two-ish weeks, I'd say.
2-ish weeks, Lisa? 3 weeks? Yeah, so it takes a little while. It's not a permanent commitment, but it's something that you can't just wash off easily. So everything that we've talked about thus far has been from plant sources. Now we're going to shift gears just a little bit to animal sources. Tyrian purple. Tyrian purple is obtained from these snails from the Mediterranean. There's a variety of different snails that are of the genus Murex, M-U-R-E-X. Those are the shells, and then this is the snail out of the shell, and you can see the purplish coloration coming off the snail. The structure of the dye from this is, it does look like indigo. The only difference between this and indigo are the two bromines. That slight a change causes, in the molecular structure, causes a significant change in the color of the dye. Now, probably the bromines are there because these are sea creatures, and halogens are present in seawater, not present so much in natural fresh water, present in treated fresh water if you've had chlorination, for example. But the bromine is there because of the seawater. So I have to read this to you because I can't remember it all. The processing of this is pretty interesting. So you have to catch the snails. You remove what's called a hypobranchial gland. Add the gland to a mixture of salt and water in a tin vessel, although it might be a lead vessel too. The description, first written description, was by Pliny the Elder in the 1st century BC, or 1st century AD. And there's some concern about whether the language that is used for tin was correct or whether it was really lead that was meant. We're going to assume tin. Okay? Then you boil it for days in open air. Some accounts suggest that you add human urine to it as well. And then you get the Tyrian purple. Like indigo, it has to undergo an oxidation to give this structure. Okay? Tyrian purple is called royal purple because of the cost. It took about 12,000 snails to make 1.4 grams of dye. You can still buy Tyrian purple. So from Kramer Pigments in 2016, just a few days ago, I looked this up. 250 milligrams of Tyrian purple costs $1,015. Man, that's pretty expensive. Cochineal. Cochineal comes from this scale insect. What's that one? It is
that what makes
Dactylopius coccus.
what makes the red in Skittles?
It could be, I don't know. I didn't check. I have to tell you, I'm not a dye expert or anything, but it's just interesting. So this insect, when it's harvested, gives carminic acid, which is a much more complex, at least initially, a much more complex structure. But it's really, if you look at it, it's just a derivative of anthraquinone once again. Nice red color though. And apparently there was an exhibit in Santa Fe at the Pasatiempo Art Museum of a whole bunch of objects that were all dyed red, including the fabric on this chair. This is a Napoleonic era chair. It was actually in his chambers somewhere, conference room or dining room or something of that sort. But a nice bright red color. Rabbit brush. I include rabbit brush because that's something local. Everybody has seen rabbit brush out in the valley. When it blooms, it gives these nice bright yellow flowers. And it can be harvested to give dyes that, depending upon how the dye is actually prepared and what it might be mordanted with, are a fairly bright yellow or more subtle shades. So those are some examples of natural dyes. And there's a lot of them that I haven't gone through. There's books that thick that deal with dyes and dyeing techniques and so on. So this just gives you a little flavor. As it turns out, though, there's not quite as many different colors available with natural dyes as with synthetic dyes. So this dashiki, for example, was not dyed with natural dyes. These are synthetic colors that are here. So the synthetic dye industry was started by Sir William Perkins before he was a sir, before he was knighted. In 1856, he was a student just like you guys, or like some of you anyway. And over spring break, he had this idea that he was going to make quinine. Quinine at that time was known to be an effective anti-malarial drug. And malaria was a problem throughout the entire world, not just in the tropics. People could get malaria in England. Mosquitoes were there, right? So as you look at the formula, C20H24N2O2, that's what was known about quinine at that time. Not the structure, but what the molecular formula was. England was the hub of the coal industry, in Europe anyway. And a byproduct of coal production is something called coal tar. Coal tar contains a number of different molecules, including this one, allyl toluidine, which has the formula C10H13N. So Perkins said, if I just double that formula and take out a molecule of water and add a couple of oxygens, I'm going to have quinine. So he took the allyl-toluidine, put it in a reaction vessel, oxidized it. Well, unfortunately, he did not get quinine. What he got instead was this tarry, ugly mass in the reaction flask. Given the current political climate, some of our candidates probably would have just taken that flask and thrown it against the wall and shattered it. But Perkins was a more measured person than that. And so instead, and because the cost of glass was a lot more expensive back then, we couldn't afford to just break something on purpose. So he took some ethanol, poured it into the flask, swirled it around, and got this beautiful purple color. That purple color was called malvine. And this is a structure of malvine. Look at all the multiple bonds that we have here, all the conjugation in that system, meaning that the molecule will absorb light in the visible region. Well, here's a picture of some of the early malvine dyed fibers that are in a museum in the UK. The synthetic dye industry. So Perkins did not finish his education. He stopped what he was doing right away because when he sent the dye to a Scottish dye company, they wrote back and said, we'd sure like to have more of that. It works really well, especially on silk, and it's going to be a lot less expensive if you can make it rather than harvest it from these Murex snails. So he stopped and created the synthetic dye industry. And England was the center of the synthetic dye industry for about 10 years, and then it moved over to Germany. There are several classes of synthetic dyes. One class is the triphenyl dyes that include such things as crystal violet and malachite green, called triphenylmethanes because they have these three rings all linked together by a single carbon. And you can see the extent of the conjugation. It's interesting to me that this is purple and that's green, even though the only difference is an additional dimethylamino group. Once again, the exact structure of the molecule plays a very important role in where the molecule absorbs light and then what color it's going to appear. So the crystal violet is used in the gram staining technique. Malachite green is used in something called the Jimenez staining technique. Malachite green also used to be used as a bactericide in aquaculture, but it's no longer being used for that. These are pretty simple to prepare, and I think we used to have a display from upstairs. It's still there. Several years ago, students in the organic class for their independent project synthesized crystal violet and malachite green, dyed some cloth, and it's up in a display where the rest of the chemistry Christmas ornaments are put on. Azo dyes are among some of the earliest synthesized dyes. Butter yellow and para red are a couple of examples. The azo group is this nitrogen double bond. These are not being used for foods any longer, but butter yellow got its name from the fact that it was the color of a good butter from dairy cows that had been eating grass, not from a feedlot, but grass-fed dairy cows. The butter that they produce is less white, more yellow. Margarine, which started to be used back in the late 1800s, early 1900s, and through the present. Margarine is white in color, but it wasn't visually very appealing. That made it look more like lard rather than butter. So addition of a small amount of a dye would allow that to be visually more attractive and give the sense that it was closer to butter. But butter yellow is thought to be carcinogenic, so it's not used anymore. And it hasn't been for a long time. Margarine is still yellow, though, because it's colored with keratin, with beta carotene. You can actually, if you do a little search for carotene and margarine, you can discover that they used to sell packets of margarine in plastic bags with a little red button that you would break that button and the carotene dye would be released and you kneaded it into the margarine to get the color of the yellow. There's even stories about kids doing that on the way home from the grocery store because it was so fun to break that disc and get the butter or get the yellow color. Para red is again no longer used for, or it's not supposed to be used for food, but apparently in about 2005, well, I should show you these colors. Sorry. Apparently in about 2005, somewhere in England, there were some samples of contaminated paprika that were found to have para red in there to intensify the color. And now everybody's favorite, or at least my favorite, the fiber reactive dyes. Here's an example of a dye, Procyan yellow. It is an azo dye. You look at this, nitrogen double bond, but it has something that the normal azo dyes do not have, and that is this dichlorotriazine at the end. The azo dyes were the fiber reactive dyes were first synthesized by Imperial Chemical Industries in London in 1956. So they've been around longer than we might have thought. It hasn't just been within the last 15 years. But these require a fixer in order to work. You buy the dye as a solid. Here's an example of the Procyan yellow. And then you just prepare an aqueous solution of it. These groups, these sulfonate salts on the chain, allow it to dissolve thoroughly in water. But in order to get this, and well, let me just go through this. Here's cellulose again. The dye fixer in this case is just sodium carbonate. Sodium carbonate is a base that will remove a few of the hydrogens from the hydroxyl groups and convert them from neutral OH to oxide anions. And then this attacks a carbon, displaces the chlorine, and we form a nice, stable, covalent bond, an ether bond between the fiber and the dye itself. And this allows us then to have brilliant colors permanently attached by covalent bonds to the cloth. And we've been doing this at Adams State. We've been using fiber reactive dyes at Adams State for a long time. Some of you might recognize this young man. This was John's organic class. And you can see the multitude of designs and types of cloth, or not types, everything was cotton, but there are some boxer shorts in there, there's some towels, there's just a variety of things in there. But if you look at this long enough, you'll probably recognize, some of you who have been here a while will recognize the students in that picture. But I'm glad to say that Dr. Leontov has been continuing this tradition of using the fiber reactive dyes as the last experiment of the organic semester, or the first semester organic sequence. The dye industry is an important economic contributor to the world's economy, expected to reach 11 million metric tons per year by 2018, and contribute more than $30 billion. And that's just for the dyes and pigments. So this is not something that we can dismiss out of hand or say doesn't contribute or it's not important for us to know a little bit about. So, dyes have been used since antiquity. The molecular structure is very important in determining what the actual color that you obtain is. Natural dyes can be obtained from both plants and animals. There's a broader palette of colors available from synthetic dyes than from natural dyes. And in many instances, especially for certain combinations like the fiber reactive dyes, they tend to be more color fast and last longer than do the natural dyes. And finally, they are beneficial to the world economy. Here's a few of the references. The top two we have available in the library, in the Nilsson Library, if you are interested in learning more about the dyeing craft. I'm not going to get a whole lot of molecular structures from these books, but a very interesting couple of books. And then a couple of other books that are of more chemical nature. And then a really interesting little pamphlet from 1921, the National Amylin and Chemical Company Incorporated, which no longer exists, wrote a little trade pamphlet on dye stuffs. And this one you have to access through the internet. We do not have that at the library. So I'd like to thank the Earth Science program here at Adams State for providing a sample of hematite, the chemistry program at Adams State for providing the ferric oxide that's used to make this just kind of light pink dye. Mr. Bev Hodder, who is a graduate from maybe 2009 or 2010. He was from Ghana in West Africa. And he's the one who brought me this dashiki. And I'd like to especially acknowledge Dr. Nearing, because he's been very good about inviting me to come back, even after I retired, to give talks every once in a while anyway. And he started this more than a dozen years ago. Was 2003 the first year? 2004? So for a dozen or more years, he's been organizing these lunchtime talks, which have been a real boon, I think anyway, to Adams State. It gives people an opportunity to not just eat pizza, but learn something over the noon hour. So I'd like to close with us just giving a round of applause for Dr. Marty.